Imagine for a moment a world where fighting global warming and cooling our buildings is as simple as, well, taking a brush and applying a single coat of paint. Seriously, no moving parts, no humming machinery, no crazy electricity bills. Just a painted surface sitting quietly in the sun, beaming heat straight out into the freezing void of space. Sounds totally like science fiction, right? Well, it's actually cutting-edge science reality.
Okay, so right now, to cool the insides of our buildings, we rely really heavily on active cooling systems, primarily air conditioners. But here's the catch. These systems require massive amounts of electricity and they use chemical refrigerants. So they end up emitting a tremendous amount of CO2 and they actually exhaust hot air right back outside. Quite literally, we are actively heating up the planet in order to cool down our homes. Now you might be thinking, well, why don't we just paint our roofs white? We already have white paint. And it's true, white roofs do help a bit, but standard commercial white paints, which mostly rely on a material called titanium dioxide, actually fall short. While they look bright white to our eyes, they secretly absorb ultraviolet and near-infrared light. Because of that hidden absorption under direct sunlight, standard white paint still heats up above the ambient air temperature. It just can't achieve what scientists call full daytime subambient cooling.
To solve this paradox, we need a passive solution, something that doesn't consume a single watt of electricity. And that brings us to the incredible science of atmospheric transmission. The absolutely crucial concept here is radiative cooling. This is a passive cooling technology that acts almost like a one-way mirror, or honestly, kind of like a magic portal. You see, our atmosphere naturally has a transparent window for certain wavelengths of infrared light, specifically right around 8 to 13 micrometers. If a material can emit its heat precisely at those wavelengths, that heat doesn't get trapped by the greenhouse effect. Instead, it passes right through the atmosphere and escapes into the near absolute zero 3 Kelvin void of deep space.
Think of it this way. Incoming solar energy from the sun is hitting a surface with about 1,000 watts per square meter. A truly effective cooling paint acts as a highly efficient shield, bouncing almost all of that solar irradiation right back away. But at the exact same time, the paint is actually taking the heat from the surface it's applied to and emitting it as thermal radiation precisely through that atmospheric sky window we just talked about, straight out to deep space. It's rejecting the sun's heat while simultaneously dumping its own heat into the cosmos.
Now, actually achieving this in broad daylight is incredibly difficult. That is, until researchers at Purdue University introduced a real breakthrough material to the world of cooling paints, barium sulfate, or BaSO4. So why barium sulfate? Well, it all comes down to its unique atomic properties. Barium sulfate has a very high electron band gap of around 6 electron volts. In plain English, that just means it doesn't absorb UV light the way traditional titanium dioxide paints do. On top of that, it has a natural phonon resonance, which is basically the way its molecules vibrate exactly at 9 micrometers. If you remember our sky window from earlier, that is perfectly aligned to beam thermal energy directly through the atmosphere. It's essentially nature's perfect material for sending heat straight to space.
To the naked eye, this material just looks like regular, clean, bright white paint. But if we were to zoom in under a scanning electron microscope, the microscopic structure is where the real magic happens. Down at that scale, you have barium sulfate particles suspended alongside tiny air voids. The interfaces between these particles and the air pockets create intense photon scattering. It's quite literally a microscopic maze of mirrors, bouncing the sunlight back out before it can heat the surface.
And the researchers didn't just mix some powder into water, right? There is some serious heavy-duty engineering here. The secret sauce requires a high filler volume concentration of 60%. But the real genius is using a broad mix of particle sizes. The particles average around 400 nanometers, but they deliberately include a wide distribution of sizes, specifically 398 plus or minus 130 nanometers. Why does that matter? Because sunlight isn't just one single wavelength. A broad mix of particle sizes scatters a much wider range of the solar spectrum than perfectly uniform particles ever could. And they bind it all together with an acrylic matrix, ensuring it can actually survive out in the elements.
Theory and lab work are great, but the big question is always, does it actually work in the wild? Well, the contrast out in the field is incredible. When placed under the exact same direct sunlight, standard commercial paint absorbed enough UV and near-infrared light to actively heat up. It actually reached 6.8 degrees Celsius above the ambient air temperature. It effectively became a heater. The barium sulfate paint, however, it reflected that broad spectrum light and maintained a temperature consistently below the ambient air.
And the reason it can do that comes down to one absolutely staggering number, 98.1%. This barium sulfate acrylic paint achieves an incredible 98.1% solar reflectance. It is bouncing practically all of the sun's energy away, coupled with a 0.95 sky window emissivity to continuously vent its own heat.
When we look at the real-world field test data, the results are just mind-blowing. Even right at solar noon, under peak blazing sunlight, the surface temperature of the barium sulfate paint actually stays below the ambient outside temperature. In fact, it dips more than 4.5 degrees Celsius below ambient. Think about that for a second. The sun is beating down on it, and the surface is literally getting colder than the air around it.
To put that into engineering terms, the paint achieves an average cooling power of 117 watts per square meter over a 24-hour period. This yields a highly impressive standard figure of merit of 0.77 out of a theoretical maximum of 1.0. That places it among the absolute highest performing radiative cooling solutions ever developed. Honestly, it acts like an air conditioner that you never have to plug into a wall.
Now, obviously, a great lab experiment isn't very useful if it just washes off in the rain. So the researchers rigorously tested its reliability. Subjected to standard abrasion resistance tests, it scored comparably to your everyday commercial exterior paint. They left it outdoors for a 3-week weathering test, and its solar reflectance and emissivity remained completely unchanged. Best of all, its viscosity profile means it behaves just like standard paint. You don't need highly specialized equipment for this. You can literally apply it with a regular paintbrush you buy at the hardware store.
So this isn't just a fun scientific trick, it's a highly scalable technology that's ready to leave the lab. What we have here is a completely energy-efficient, environmentally friendly temperature control solution. It requires exactly zero electricity, it uses exactly zero toxic chemical refrigerants, it operates purely on the physical laws of the universe, fighting the urban heat island effect simply by sitting there.
The applications for this are practically endless. Think about the massive energy savings for commercial and residential buildings. You're talking about drastically slashing air conditioning bills. Imagine industrial facilities that generate massive amounts of heat being passively cooled. Or think about the global cold chain. Refrigerated trucks transporting our food and medicine could be coated in this paint, taking a massive strain off their cooling engines.
I really want to leave you with a thought to ponder. We started this explainer by talking about the paradox of cooling our world by actively heating it up with ACs. But what if we completely reverse that? What would happen to global temperatures, to our strained energy grids, to our overall carbon footprint if every major city on Earth simply painted its rooftops with this ultra-white paint? It's a staggering, beautiful possibility. A cooler future might literally be just a brushstroke away. Thanks for joining me for this explainer, and keep looking up.